So I'm going to present Hnefatafl. This is the first time it's been implemented on the FPGA, on any FPGA. It's better known as Viking Chess. As you can see, we have a simple gameplay demo. Accompanying this is our web interface. Right now you can see we have a spectator mode. Here's a diagram of kind of how it works. We're using Socket.io to communicate with a Node.js backend running on an Amazon EC2 server. And we use serial communications between our FPGA and the Node.js server to transfer the necessary data between the FPGA, the host computer, the web server, and then the end user's browser. So in this game, every piece moves like a chessboard, and white is outnumbered 2-1. White has to get the king in the center square to the corner, and black has to try to surround white's king. So as you can see, we are, here again is that diagram, we are basically replicating the game state from the FPGA to the web interface, but the FPGA is actually doing all of the processing. The web interface is just for graphics. This demonstration is of our AI. So as you can see, black is playing as an AI. We actually have several different game modes. You can play 1 or 2 player, local or over the internet, and 1 player is utilizing the AI. So right now we're accepting moves from a Python-based AI. Tom's going to talk about that.
Major challenges I encountered when in implementing the AI were mostly based around the way AIs are normally implemented, based on and also how one would implement things on an FPGA. The difference being that classically AIs are implemented in a very sort of sequential way, and almost all writing on AI implementations is written in the assumption that all things will be made sequentially. And in general, that sort of needs to be the case. There's not a lot of parallelizable things to be done. So for the most part, implementing that on an FPGA, while certainly possible, is difficult, since it involves creating very large data structures and then sort of juggling them around in memory, which is difficult for the FPGA with its limited memory and resources for those sort of tasks. What the FPGA is good at is parallelizable things. So we focused on that for things that that could be done there, whereas for the AI, we sort of outsourced it to a PC coprocessor that would generate the AI moves when they were requested from the FPGA and then send them back, which sort of vastly simplified integrating an intelligent AI into the system. A lot of research has been done into FPGAs for game AI, however. However, usually this is mostly in the instance of an FPGA being used as a coprocessor for a sequential AI. The way this works is that the FPGA is used to generate move lists. I talked earlier about how I generate the move sets in the AI, an improvement that could be made is that I could request the move set from the FPGA, which can generate it much faster, because the move set generation is a very parallelizable thing. If you can check every piece's move set at the same time, then there's no reason not to, because the results of each check don't affect each other. So you can do it a lot faster if you do it in logic versus doing it in sequential computer code. However, we didn't have time to implement this.
So this is an example of the game actually ending because white moves the king to the corner. All the game logic for this game is implemented. You can find the rules online. Here's a detailed web demo. So Evan here is going to select 2-player mode for the internet remote. He's going to play as black. That's the color of the FPGA that he's selecting right there. And as you can see on the 7-segment display, there's a game code. He's going to give that to Tom, and Tom's going to type that into the web interface. And basically, Tom is going to be able to play against Evan. All the processing is done on the FPGA entirely. So Tom's browser receives the state from the FPGA that Evan's playing on, and black moves first, so Evan's going to go ahead and move. He uses the arrow keys of a USB keyboard. The graphical output is 800 by 600 resolution, I should mention. So he's going to move a piece, and then that change is going to be reflected on Tom's screen. And right now you can see he can't move diagonally because we validate that his move is correct. So it's White's turn. The web interface will actually show this in the bottom right, and in the bottom left it shows who that player is. So Tom's going to use the keyboard to control where he'd like to go. And that change will be sent to Evan. And the really cool thing is you can actually spectate. So hundreds of people can join in and watch this game. Now they can't play for Tom, but they can certainly watch. And here's a demonstration of the Spectators. So this is my laptop, and I'm going to join in on this game and watch them play from across the room, or really across the world if I wanted. And I can just join right in the middle of the game and everything works. And the way this happens is, again, the serial communications of the FPGA to Python, communication of Python to Node.js using Socket.io client for Python, and then the communication of Node.js to the browsers using Socket.io. This is a demonstration of multiple spectators, so as I said, this scales to as many spectators as you like, and here the game ends and the clients are told of that. We have a lot of game logic. It gets kind of complicated. You can actually move between two pieces and have your piece be safe since you initiated that move. So here White is going to move between the two black pieces. And our cleanup code is going to know, our black's moving between the two white pieces, our cleanup code knows not to delete that piece. Here are two different web games running simultaneously, so we can actually support, theoretically, an unlimited number of FPGAs all playing simultaneously in different channels, and that's what that code on the 770 display is for. Here's a little bit of an overview of the game logic. And I'm going to talk in more detail about that now.
A single finite state machine that's composed of a bunch of different other state machines within it. And our game basically goes through a loop of starting with initialization, and then we go into the loop of allowing for move selection, then move validation, and then if the move is valid, then we perform that move, and then we have to do a little bit of cleanup. And that involves making sure that a piece hasn't been jumped, and if it has, removing it from the board and detecting whether the game is ended or not. So I want to talk a little bit about how move validation and selection works. So basically we have a game board, and it's 11 by 11. And whenever someone performs a move, say to go from this square to this square, with squares in between, of course. We're going to have to make sure that there aren't any pieces in these squares. Because if there are, then obviously they cannot move from this square to this square. So we have a coordinate system. This is 0, 0, and this is 10, 10. And what happens is, when I select a piece in this square and say I want to move it to this square, we're going to go through a series of states in our state machine that walk us along this path. So first, we're going to check in which direction we're moving. And we're either going to move up, left, down, or right. Because the only valid moves are moves that a chess rook can make. And we are going to set an offset x and an offset y based on which way we're moving. So if we're moving to the right, our offset x will equal +1, and our offset y will be 0. If we were moving up, our offset y would be -1, and our offset x would be 0. We're going to repeatedly add this offset to the current coordinate, starting at what's called sx, sy. And we're going to do that until we reach mx, my. S stands for select, M stands for move. As we add OX and OY to SX and SY, we traverse along the path that goes in a straight line to where the user is trying to move. Each time we hit a square, we read the memory on the positive edge of the clock, and we ask whether there's a piece in that square. And if there is, we say the move is invalid. But if we reach MX, MY before we see any other piece, and MX, MY does not contain a piece, then we know the move is valid. You can stop recording. So we have our game board. A user makes a move, and we need to determine now whether that move has affected any of the pieces on the board. So we're going to start at coordinate 0, 0, and we're going to traverse all the way to coordinate 10, 10 by scanning first horizontally and then vertically. Each time we look at a square, we see if it's blank. If it is blank, we move to the next square. If there's a piece in this square, we determine what type of piece it is. For the king, we will first check whether the king is in the corner. If the king is in the corner, the game ends, and white wins. Otherwise, if it's a king, we check if it's surrounded on all 4 sides, where the walls and certain other squares in the game count as occupied. If it's not a king, and it's just a normal white or black piece, we simply check whether or not it's surrounded on 2 of 4 sides that are across from each other. If it is, we remove that piece. If it's not, we continue traversing the board. Once we reach 10, 10, we're done. One very important thing to note is that it is legal to perform the following move. Say we have a black piece and a black piece, and white moves between black and black. This move is completely legal, and next time we scan the board, say when black then moves over here, we need to make sure that we don't remove this white piece, since white did move on his or her own accord to this spot. To do that, we have to maintain some extra state. We found that randomly move validation would fail, and there was really no pattern to how it was failing. But what we discovered after a lot of trial and error was that OX and OY were 2-bit registers. However, the coordinate system for the game was based on 4-bit registers. So, when we were repeatedly adding OX and OY, we were adding a 2's complement representation of -1 when we go left or up. That 2's complement representation, 1, 1, was getting added to 4-bit numbers. And of course, 2's complement no longer works in that case, and we were experiencing erratic behavior. After a lot of trial and error, we discovered that this was the cause for our problems.